Welcome, welcome to Unit 7, the last whole unit you will have to watch by yourself, because Unit 8 we will do half in class. Welcome. What is wrong with me? Oh my gosh. Alright, here we go. Unit 7. We got equilibrium. Ready to rock. I'm hydrated. I'm caffeinated. Let's go. Are all chemical and physical reactions reversible? Nope. Which of the following describe a reversible reaction which is irreversible? You mix salt with water and watch it dissolve. Several days later, much of the water has evaporated. I would say that is reversible. Can definitely get it back. We're just talking about physical chemical changes right now. You drop a tail of baking soda into a cup of vinegar, tons of bubbles appear. You have made something new. So that is irreversible. That's a hard word to spell. A and B mix. You mix A and B together. At 10 minutes, you observe 100% of A and B have become C. That's irreversible. X and Y make Z. You mix X and Y together. At 10 minutes, you observe that the concentration of X and Y is 80 and Z is 20. It's not gone to completion. Later, it's still not gone to completion. It's probably at equilibrium. This is reversible. Minute reactions are reversible. To indicate this, a special type of arrow is used to separate the reactants and products. A reversible reaction starts with the forward reaction until the concentration of products reaches a level that the reverse reaction will begin with until the forward equals the reverse and the equilibrium is established. Mark the following statements as true or false. Equilibrium is reached when all of the reactants have been converted into products. True or false? False. They don't have to all be gone. At equilibrium, there could be more product than reactant. That's true. At equilibrium, there could be more reactant than product. That's true. At equilibrium, the rate of the product becoming the reactant is equal to the rate of the reactant becoming the product. That's true. It's kind of this graph right here. At equilibrium, the reaction rate of both the forward and reverse reaction is 0. False. At equilibrium, the concentration of product and concentration of reactants are unchanging. Right here, check it out. True. Consider the graph to the right. What is the balanced equation for this reaction? Well, I know that my reactants are NO and BR. So I have NO plus BR2. I know that my product is NOBR. Now I have to look at how are they changing. Well, I can see that NO is going down about half as much as BR2. And NOBR is kind of going up twice as much. So I could also just balance it. But look at it with the graph too. BR2, 2, 2. So NOBR is going up twice as fast as BR is going down. Or just balance it. Reactants start with the concentration, products don't. Add a dotted line to the graph showing the time where equilibrium was reached. Well, I would say right about there, where they go parallel. Circle the point in time on the x-axis that the rate of the reactant to product became equal to the rate of the product goes to reactant. Well, that's kind of silly. It's going to be the same. Sketch a graph of the same reaction if you began with 100% NOBR, 0 NO and BR2. Label the lines on your graph just like the one above. Well, it's going to be the reverse. So if I start out with NOBR, NOBR is going to go down. So here's my NOBR. I'm going to start out with 0, but I know that the NO is going to have to go up higher because NO is a 2 coefficient than my BR2. So what's the balanced equation? 2NO Br is in equilibrium. I probably should have put this one in equilibrium too. With 2NO plus Br2. Okay, flip the page. In the graph to the right, I should probably say the graph to the right describes this equation. 2SO3 is in equilibrium with 2SO2 plus O2 minus, add the following labels in the appropriate locations: equilibrium, reverse reaction, forward reaction, and label these. Well, I obviously know the equilibrium. This is a weird one. But equilibrium is where it's flat. So, reaction rate. So, if this is the whole reaction, my forward reaction has to be going down. So that is going to be the one that's making my SO2. So this is going to be 2SO3 yields 2SO2 plus O2. And then my backwards reaction is going to have to be 2SO2 plus O2 yields 2SO3. So this is forward. This is backward. That's all I had to label. At the start of this reaction, the reaction rate of the reverse reaction is what? Well, here's backward. It's 0. Why? Well, there's no product yet. There is no product to turn back into reactant. The reaction is at equilibrium when the rate of the forward reaction is greater than, less than, or equal to the rate of the reverse reaction. Equal to. For the reaction depicted in the graph, circle the time or block of time on the x-axis when the reaction rates of the forward are equal. Well, that's all of these. More product is being made than reactant when the rate of the forward reaction is, it's going to have to be greater than the rate of the reverse reaction. For the reaction depicted, is there a time or block of time when there is more product being made than the reactant? If so, draw a square around it. Well, that's going to be here. There's more being made. More reactants being made than the product when the rate of the forward reaction is less than the rate of the reverse reaction. For the reaction depicted in the graph, is there a time or block of time when there is more reactant being made than the product? If so, use an arrow to point to it on the x-axis. No. There is no time in the graph where that's happening. The rate of the forward reaction is always higher. So, none. And like I said, this is kind of a weird one. Flip it. So, the reaction quotient Q provides information about the concentration at any time, and it's usually at the beginning. So, for the two graphs, label the parts of the graph where Q equals K and where Q does not equal K. Well, I know that Q equals K where it's at equilibrium. I know that Q does not equal K when it's at any other point. Same thing over here. Q does not equal K. Q equals K. Complete the table, making the equilibrium expressions for each of the reactions. So I have to do a Kc, a Kp, and a Qc. Here we go. So Kc is going to equal products of reactants. So it's going to be concentration of HF squared over concentration of H2 times the concentration of F2. If I was writing a Kp, Kp would equal pressure of HF parentheses squared over pressure H2 parentheses over pressure F2 parentheses. And then my Q is going to be the same as my K. So my Q should be exactly, these are going to be the same. I'm not going to rewrite that. Just with Q instead of K. Kc for this one, I have Kc equals concentration of NH3 squared over concentration of N2 times the concentration of H2 cubed. Kp, here come my parentheses, equals parentheses pressure of NH3 squared over parentheses N2, or should I say PN2, over parentheses PH2 cubed. And then my QC is going to be the same as my KC. Lastly, I have this one. So Kc equals concentration of CO2. Solid, not included in the equilibrium expression. Therefore, Kp equals pressure of CO2. I'm still putting it in parentheses. And then my QC is going to equal the same, concentration of CO2. For the reactions above, put a star beside any homogeneous equilibrium reactions. What is different about writing equilibrium expressions for heterogeneous equilibrium reactions? Well, which ones are homogeneous? Well, the homogeneous ones are going to be the ones that, oh, there already is a star. The homogeneous equilibrium expressions. What the heck? There's already stars there. That's kind of weird. What's the difference between writing equilibrium constant expressions for heterogeneous equilibrium? Well, if it's heterogeneous, solids and liquids aren't included. That's all they're saying here. It's a weird way to say it in your Kc or Kp. So solid liquids aren't included. That's homogeneous. That's homogeneous. That's kind of weird that the star's already there. Fill in the missing information in the table below. If Q is less than K, then there is a higher concentration of products or reactants than there is at equilibrium. Well, if Q is less than K, it shifts to the right, because that's right, a queen's less than a king. Therefore, my reactants are going to be favored. At equilibrium, I know that K equals Q. K equals Q. And if I have my products favored, that means it's shifting, the higher concentration of products than there is at reactants. That means it's going to be shifting to the left or reverse. That means that K has to be less than Q, or Q has to be greater than K. Here we go. K 1.6, Q 1.5. So Q is less than K. That means it's shifting to the right. And that means there's going to be a higher concentration of reactants, which is causing it to shift to the right. In particular reaction, QC equals 1.1 times 10 to the second. You begin the reaction. After 2 minutes, you calculate the reaction quotient and find Q is 4.8 times 10 to the second. Based on the information, you know the reaction has not reached equilibrium. 20 minutes later, because it's not equal, you measure the reaction quotient again. You expect that Q is going to equal 4.8 divided by Q is 1.1 to the second. Which one do we expect? Well, as it's getting closer, it should be moving and getting closer to equilibrium, so my Q should be getting closer to my K, so I'm going to expect it to be closer to the K. Once the reaction quotient is equal to the equilibrium constant, the reaction quotient will stay the same. What are the units for K and Q? None. Flip the page. Wait a second. Something copy weird here? Unit 7. Unit 7. Oh. Here we go. It's just the way I stapled it. Sorry. The The following reaction is carried out in a 1 liter flask at 25 degrees Celsius. 3.00 times 10 to the negative second moles of NO2 are added to the flask. At equilibrium, 2.36 times 10 to the negative second moles of NO2 and 3.2 times the negative second moles of N2O4 remain. Calculate the Kc for this reaction. Well, first we need to write our K expression. So, Kc is going to equal concentration of N2O4 over the concentration of NO2. So Kc equals, my N2O4 is 3.2, let's see, 3.2 times 10 to the negative second. So 3.2 times 10 to the negative second over concentration of NO2. I can also just do moles, I guess. I don't really even, it is one, because divided by 1 liter. So that is molar. So I have 3.00, wait. So I have NO2. Oh, at equilibrium, 2.36 times 10 to the negative second is here. 2.36 times 10 to the negative second. Calculate K for this reaction. So 3.2 e negative 2 divided by 2.36 e negative 2. Oh, you know what? That should be squared. This should be squared. So divided by 2.36 e negative 2 again. Yikes. Divided by 2.36. So for K, I got 57.5. On this one, at 100 degrees Celsius, the equilibrium partial pressures for the following reaction are this. Calculate Kp. Kp, here come parentheses, equals, parentheses, pressure of N2 over parentheses, pressure of H2 cubed over parentheses, pressure NH3 squared. So Kp equals, my H2 is I guess I'll do N to keep it all the same. N2 is 0.37 ATM. H2 is 0.07 cubed, and divided by NH3, NH3 is 0.20, and that's going to be squared. Solve that, and you should get Kp equals 3.2 times 10 to the negative third. Okay, ATM. Consider an aqueous solution containing oxalic acid, which is this, with that molarity, fluoride ions, and hydrofluoric acid, and oxalate ions. Kc is 2.1. Determine whether the system is at equilibrium or if the net forward reaction is occurring, if the net reverse reaction is occurring. Support your conclusion with an appropriate calculation. So for this, I'm going to have to solve for Q. So here we go. Q is going to equal my concentration of HF squared times the concentration of C2O4, 2 minus, divided by, I'm on the screen, yep. Concentration of acetic acid, this isn't acetic acid, it's H2C2O4, times F squared. Sub in everything I got. So my HF is 3.5 squared. C2O4 is 0.28 divided by 0.76 times 8.26, and that one is going to be squared. So Q ends up being 0.063. 6. Therefore, Q is less than K, so it's going to shift to the right. So, forward is favored. So, forward is favored. All right. Flip it. When at equilibrium, if the concentration of the product is more than the concentration of the reaction, K is greater than 1. Show this to be true. Well, I guess I could just write K products over reactants. K equals. This just means that my products has to be larger than the reactants. I don't know what else they want me to show here. The concentration of reactants is more than the reaction. Q is less than 1. K is less than 1. Okay. So K equals concentration of products over concentration of reactants. That means this is going to be larger on the denominator. This is going to be smaller on the top. So the fraction is going to be less than 1. And if K equals 1 divided by 1, then that equals 1. So, fraction is 1. Okay. Here we go. Reaction 2H2O. K is this. K is greater than 1. What species will you find the most of in the highest concentration at equilibrium? Well, if K is greater than 1, that means I'm going to be favoring my products. Therefore, that's going to be H2O. K is less than 1. I'm favoring reactants, which is going to be NO and Br. Specifically, 2 times as much NO because of the coefficient. Which of the following reactions will produce the least amount of products at equilibrium? So I have A, I've got B and C. I got to compare my Ks. So my smallest K is Kc. So that's going to be reaction C. The most products is going to be the one with the highest K. So that's going to be A. At equilibrium, which one's going to be the closest to 50%? Well, that's close to 1. So that's going to be B. It's going to be B. Okay. Flipping it. Consider following reaction. Determine Kp for the 3 following manipulations of the above reaction. Okay, so this one I have flipped it. So it's going to be 1 over Kp. So 1 divided by this, which is going to equal 4.55 times 10 to the third. This one, what did I do? I divided it all by half, I think. So 2 divided by 2 is 1, half, half. This is where my Kp, that means I raise my Kp to the power of 1/2. So if I do the 2.12 to 1/4 to the power of 1/2, that ends up being 0.0146. This one, double, double, double. That means my Kp is going to be squared, which is going to equal 2.22 times 10 to the 7th. Okay, easy peasy. Calculate the value of K for the reaction at 25 degrees Celsius. Using the following information, show your work. Here's Kp1. Here is Kp number 2. So I need to get this reaction. I need to get 2NO on the other side. Therefore, that first reaction I have to flip. So it's going to be N2 plus O2 is in equilibrium with 2NO. So that makes my Kp1 1 divided by 1 times 10 to the 30th. The second one, let's see. So I need to get N2 gone. So I need to flip this one as well. So 2NO Br is in equilibrium with N2 plus Br2 plus O2. The N2's gone, the O2's gone, and that leaves me 2NOBr, yield 2NO plus Br2. Perfect. I flipped that one as well, so that's also going to be 1 divided by 2 times 10 to the negative 27th. So for k total, I have to do 1 divided by well, that is just 1 times 10 to the negative 30th. So this equals 1 times 10 to the negative 30th. This equals 1 times 10 to the negative. Oh, that's a weird one. I have to actually figure that one out. So this ends up being 5 times 10 to the 26. And then to combine your KPs, you actually multiply them together to get your K total. So K total equals 1 times 10 to the negative 30th times 5 times 10 to the 26, which ends up being 5 times 10, 26, 30, 5 times 10 to the negative 4th. So that was a little bit of Hess's law, a little bit of everything, and manipulating K. How much time do I have left? I have 2 minutes left. Let's do one ice table. Following reaction, it was carried out at particular temperature. You had 2.67 moles of CO2. That's going to be of CO. That's going to be my initial. And 2.67 moles of H2O into a 750 milliliter container. Yikes. Calculate the equilibrium concentrations for all of them. I'm trying to figure out if I want to do the molar now or later. I'll do it later. I'll just do moles and then change it later. No, that's silly. Nah, I'll do it now. I'll do it later. So 2.67 moles, 2.67 moles, 0, 0. So this is going to be minus x, plus x, plus x, 2.67 minus x. This is going to be 2.67 minus x, x, and x. K equals concentration of CO2 times concentration of H2 divided by concentration of CO times concentration of H2O. Some of my numbers, so K equals x squared over 2.67 minus x squared. So I'm going to take the square root of that whole thing. So K equals x over 2.67 minus x. Is this going to be quadratic formula? Oh, they gave me K. No. So 3.58 equals x over 2.67 minus x. So I'm going to solve for x. So multiply by x. 3.58 times 2.67. So that means that 9.55 minus 3.58x equals x. Add x. So 9.55 equals 4.58x. And 9.55 divided by 4.58 gives me 2.08. So x equals 2.08. So calculate equilibrium concentration of all of those. So now I have to do 2.08 divided by 0.75 because I didn't do the molar. That was just moles. So divided by 0.75 gives me 2.78. So I have 2.78 molar. So this is 2.78 molar. This is 2.78 molar. a second. That does not make sense. I made a mistake. I have that times that, x squared over 2.67 minus x something is weird. 2.67 divided by 0.75. What if I did this all as molarity first? 3.56. This might make it easier. 0.56. So this would be 3.56, 3.56. So K would equal x squared over 3.56 minus x squared. So if I redo this, 3.58 would equal x over 3.56 minus x. So multiply 3.58 times 3.56. So that would give me 12.74 minus 3.58x equals x. So add 3.58, 12.74 equals 4.58x. And then 12.74 divided by 4.58, that gives me 2.78. So that actually gives me that's still giving me the same answer. Technically equilibrium. Because if this is 2.78, 2.67, oh, you know what? That's actually better. So 2.78 molar. You have to put this in molar first, because if you don't, the 3.56, it's going to give you a negative. So 2.78, 2.78, 3.50 minus 2.78. 3.5 minus 2.78. That makes this 0.72, and that makes this one 0.72 molar. Does that make sense? Well, K is large, products are larger than that. Let's just multiply it out and make sure that actually works. 2.78 times 2.78 equals divided by 0.72. Yeah, I think they have a mistake on here. The key that they gave is weird. I'm going to come back to this when I have more time. But I think there's something weird about this problem. So, what's the second one? We're going to try this one at the beginning of the next part 2 of Unit 7. There's something wrong with these numbers. Oh, I see. On their key, they wrote 2.76 instead of 2.6. Look at this, guys. This problem is jacked. Because they wrote 2.67, then they wrote 2.76. I did it. I did my work right. But the way they have it set up, there's no way to get a good answer. That's a bad problem. Well, hopefully this next one will be better. We're better than this.